Okay, so electric current. Here's a picture of a circuit concept. There you go. And this is my introduction to just the concept of electric current, a concept that is probably reasonably familiar to you. Anybody who has ever plugged in a light bulb or any other device, you've experienced something with electric current. When we got ourselves shocked on the Van de Graaff generator, those were electric currents actually too, even though they were very short, light pulses, but they were still electric current. Most of the time though, we think of electric current when it comes to circuits, okay? And we'll learn more about these particular terms as a circuit, but essentially, when you close the switch, an electric current starts to flow. And what you're going to learn in this unit, in this section, is the details of what's going on with electric current. Not just the very simple parts that you probably did in elementary and middle school maybe with some experiments, but the details of energy transformations that take place and how it actually works. Okay? One of the things that you can get from this picture is that something is flowing around and that it is going into a part of this apparatus that is producing light and going back into here, sort of like disappearing into the middle of this thing and then somehow reappearing and coming out again, right? And this represents what's basically happening in many types of circuits that involve a battery, right? That would be a battery over here on the left, okay? So the things that are flowing in this picture, by the way, would probably be what? What are the things that are moving? Possibly electrons, right? In fact, yes, in this picture, these red dots represent electrons. Now, I know that probably because they are going away, they seem to be going away from what is like a negative sign here, right? So kind of repelled by the negative sign, and they are attracted, until I close the circuit, they seem to be attracted around and around and around to the positive over here, right? So it suggests that these are charges and that they're negative. Okay, they're flowing around in the circuit. The reality of it is we can't actually see the charges, and these kinds of facts have to be deduced scientifically about what is actually happening. And as we'll learn later on, it wasn't until long after the first electrical circuits were produced and studied, it wasn't until long after that we actually knew that it was the negative electrons that flow in a circuit. We will see that as we study electricity, we will always talk about it in terms of positive charges moving. But in fact, it is the negative charges that move in most circuits, but not always. So it's not completely wrong to talk about positive charges moving in a circuit. Okay, so what is electric current? Electric current basically is the motion or movement of electric charges or flow of electric charge and this happens in lots of different materials as we have seen. It can happen in a solid, such as we saw or we have experience with in electrical wires and the conducting apparatus in parts of the Van de Graaff generator. Electric charge can flow in a liquid, which is the case, for example, with batteries, or the correct word that we will usually use is a cell. I don't mean a biological cell, but we might call a chemical cell or battery cell. The word battery actually means when you put several cells together. Okay, but that's just a technical thing. We still use the word battery even for a single cell sometimes. And also, current can flow in processes like electrolysis, which you can read about, or maybe we'll do an experiment on at some point. And current can flow in gases. Okay? Examples of current flowing in a gas were the gas discharge tube, the lamp that I was using with the Van de Graaff generator, and you saw it flickering, right? Even lightning itself and the sparks that you see jumping through the air, that constitutes an electric current, and it's flowing through the gas, the air, such as lightning. Okay? So how does it happen? How does current flow? Why does it flow? Well, there has to be a reason for those charges to move. And the reason is that they are experiencing a force. So charges move because they experience a force that pulls them, you might say, by the electric force, or that is, they are reacting to an electric field from an electric field. And we know all about electric field. And one of the things that you know about electric field, by the way, is that yes, okay, we can pull a charge with an electric field, but where does the electric field come from? How do we even get an electric field to begin with? What are the things that we had to do to get an electric field? How can we make an electric field that will then be used to produce a current? That's a good question. We've seen it. So where did we do? What did we actually do? Give me one example of something where we created an electric field, and therefore such a field might be used to make a current. Yes, Hugo?
Rubber glue on felt.
Yes. When we rubbed the cloth of some kind onto one of the rods, actually it doesn't matter which one we rub back and forth. The point is there was some motion between them, creating friction, and it's possible, for example, the rod became negatively charged and the fur maybe became positively charged. And then when we separated the charges, and that's the key element, right? We separate the charges this way, bringing the fur further away perhaps. And that's a charge separation. And the reason why that makes an electric field is because, as you might imagine, if you put a test charge right there, it's going to be repelled from the positive charges and attracted to the negative charges, and we have that electric field. So, answer to my question is, we create a charge separation. That is the key to creating electrical fields. Now that might seem rather obvious, and good if it is, but it is fundamental to every aspect of electricity and electrical circuits that involve flowing current. Somewhere, somebody had to separate charges to make this happen. And sometimes it's not obvious where that happens, but I also want to emphasize that no matter how abstract and, let's just say, at a higher level our electrical discussions go and circuits and so on, ultimately it all comes back to the basics of moving charges, experiencing forces in electric fields. And that's why we learned the details of that first, because it is necessary to understand that if you're going to understand everything else that follows. Okay. So, you also are aware that in some materials you are able to cause the current to actually flow sort of spontaneously. We separated charge, but if we touched a metal object, we knew that the charge could flow onto that metal object, off of it kind of freely. And this process of flowing charge is conduction. It's when charge flows in a material, right? Oops, wrong color. So the flow of charge, I'll even go so far as to say the free flow of charge. Usually we restrict that to flowing in a material substance. Like a solid or a liquid, or even a gas, right? Okay? And so when charge can flow in a material, we say that the material conducts the charge, allowing it to be led from one point to another. Okay? And I call it the free flow of charge because if it's not flowing very easily, well, then we would say it's not a very good conductor of charge. The most common way we think about conduction is in materials that conduct it well, and those are metals. Okay? Conduction in metals. How does it work? That's one of the things we want to look at. And how is it different from other types of materials that might conduct electricity? Metals are very special. Metals contain many so-called free electrons. Electrons that are only loosely attached to the atomic crystal lattice structure and the atomic nuclei or ions that exist within the structure of a metal or solid. They're loosely attached and they are more easy to flow along between and around the ions, kind of like you can see in this picture down here where we have the ions. I call it an ion because there is the nucleus of a metal atom surrounded by tightly bound electrons that cannot flow freely because they are attracted to that nucleus. The nucleus is, of course, as you know, positively charged. But the outer electrons are kind of shared among all the different ions and can kind of flow freely between them. So in other words, the overall charge of the piece of metal is neutral. But if we imagine it is a system composed of some positive ions surrounded by a whole bunch of extra electrons, those extra electrons are not strongly attached to any particular ion. They are attracted more or less equally to all of them, and so they just kind of hop between the ions, flowing freely around. So these free electrons are what we call the conduction electrons in a metal. These are the electrons that can more or less flow freely through the metal. And that flow, when an electric field is present. Okay, conduction electrons are the electrons that flow when an electric field is present. Again, in this picture that I have here, you can see the simulation of electrons in this metal, and that they are more or less free to wander between the different ions that are there. But notice that on average there seems to be a gradual motion toward the right. It's a little bit hard to see in this simulation, but the idea is that you can see some electrons kind of popping in over on this side, over here, and gradually working their way and leaving on this side. But in between, those electrons have a sort of random motion too, kind of bouncing around in different directions, not always going in a straight line, right? So the actual motion of an individual electron in a metal is kind of haphazard. And if we follow the path of an electron throughout the course of its motion, it might look something like this. Kind of like pinball, right? And of course I'm making this up. But on average, they might even go backwards once in a while and eventually make their way out of the metal. Okay? So the average velocity over the long term of the electrons in the metal is what we call the drift velocity. And it represents basically what we normally think of as the overall current. The overall current. Sometimes called the drift speed or average speed of these electrons. Again, some of them are going backwards, some of them forward sometimes, but on average they tend to go in one direction. Why does it even happen? Well, what must be true if these electrons are gradually moving from the left to the right with the drift speed? What must be causing them to do that? What causes current?
Difference in charges.
Doing something about the fact that they are charges? But why would they move?
Charge separation.
Charge separation.
Okay, and a charge separation would cause what to be there? Electric force, electric field, right? So in other words, we know that there must be, inside this metal, there must be an electric field that is causing charges to move, right? Okay, now I'm being a little bit maybe informal about this because the arrow I'm drawing here is the arrow of the direction of the charges flowing, right? But if that's the electric field, so I'm going to fix this. If that were the electric field, then electrons, would they be pulled to the right in this picture or left? Would electrons be pulled to the right by an electric field that is to the right? Yes, positive charges would be pulled to the right in an electric field that is pointing to the right. So if it's a negative charge, it would actually go to the left, wouldn't it? That means that in actual circuits, there is an electric field that is going in one direction, and the flow of electrons is actually in the other direction. So I'm going to have to fix that. So our electron flow is opposite to the direction of the electric field. So, okay, we have an electric field going to the left in this picture, and the electrons drifting to the right. Very important concept. Again, historically, physicists did not know that the flow of our most common kind of current in wires was actually opposite the direction of electric field. If this is the direction of our electric field, to the left, then you said that electric field must be caused by a charge separation, which we could make, for example, by rubbing a rubber stick against a piece of fur, and then you would hold that piece of fur on each side of a conducting wire, right? So this must be like maybe a wire, and on one side you touch the rubber stick, and on the other side you touch the fur, and electrons that manage to get off the rubber stick will flow through the conductor all the way to the other side, right? We said most of the time the rubber stick was negative, and so that means that the electrons would be flowing toward or away from a negative charge? Would electrons flow toward or away from a negative charge? Toward or away from a negative charge? Are electrons positive or negative? So would they flow toward another negative? No. So if these electrons, and if the drift, oops, I erased my D a little bit there. If the drift is to the right, then the electrons are probably flowing away from a negative charge. I'll draw that with a big negative sign. And they're probably flowing toward a positive charge. And again, where do you get that negative and positive? Could be various ways that we've seen where we can separate charge. Bottom line, though, is that if we separate the charge and we put a negative over here and a positive over here, if any of those negative electrons manage to get into the metal, they will be pulled across, right? In fact, the metal itself, because it's a conductor, will take these electrons that were already in the metal and they will easily flow in this direction, creating a deficit on this side, right? An imbalance of charge, which then will pull electrons over to here. So it's almost like water flowing through a hose, right? As soon as you turn the hose on, water comes out if it doesn't have to fill in the gap. Imagine a hose full of water. Imagine where people pumping gas. You pump gas, as soon as you pull that little trigger on the gas pump handle, gasoline comes out because it's already full of gasoline in the hose, right? So it just immediately starts moving as it goes through the wire and comes out the other side. Now, moving right along. Conduction doesn't have to be just in metals. We also said it could happen in gases. Examples I already gave were lightning, gas, fluorescent tubes or discharge tubes, gas discharge lamps, like fluorescent tubes that we have in our classroom. And you should know these examples. In liquids, I said what earlier? What was an example of where we would have conduction in a liquid? Okay, batteries or cells. Also, electrolysis. And when I say cells, electrolysis is when you can separate out water into hydrogen and oxygen. Okay, we'll probably see examples of that at some point. I didn't want to go into too much because I think that's a potential way, investigation maybe that you could do for your IA or something. And by the way, speaking of IAs, I will be looking through everything this week and giving you a whole bunch of feedback while you're on a China trip. Okay, so can there be a current in a vacuum? Well, technically, it wouldn't be a vacuum if there's anything in there, including the charges, right? But in a situation where you have a vacuum and then you create some charges that are free to flow and float around in a vacuum, yes, you could have a current. Okay? So the answer is yes. For example, in space, from the sun, there is something called the solar wind that evolves charged particles from the sun that are streaming away from the sun with a lot of kinetic energy, and they are just flowing. They are not necessarily attracted by an electric field, by the way, so it's a special case. They're just flowing. They're out there moving. Also, something called a cathode ray tube, CRT, is an example. And maybe your great-grandparents had one. It is a glass tube that the air has been sucked out of, or maybe your parents, actually. I know I had one. You suck the air out of it, and you create an electric field in it with some various electronics. And you heat up a filament that gives off electrons, and they fly across the tube, and that was the basis for most televisions. Before the advent of flat panel LCD screens, right, most TV tubes were just a big glass tube inside of a big wooden box or plastic box. You ever seen an old-time TV, right? And so basically, a cathode ray tube has something called an electron gun, producing electrons, and there's a thing that makes an electric field that accelerates the electrons across this space where it smacks into a fluorescent screen and gives off light. So just want to give you an example that you can have a kind of current in a vacuum, but we wouldn't necessarily call it conduction because it's not going through any kind of medium. Okay, so we've talked about current and what current means in a sense, right? And examples of current. But now we need a formal definition of current. We said that current is basically, as we said, the amount of charge. It's an amount of charge. And I would say net charge, because you might have both positive and negative charges, but they will cancel out, right? Okay, so the amount of net charge flowing past a given point. This is very long and wordy. In a unit time. In other words, amount of charge per unit time passing through a point in a wire, for example, right? How many coulombs of charge pass through this point in the wire each second? That would be the current, okay? Quotation marks, charge per unit time. Well, the symbol for charge is Q. Now, I would say that it could be an individual charge, but in this context, it usually means the total amount of charge that is transferred, okay? Amount of charge that is transferred, divided by the amount of time that it takes to do that. And the symbol for this is I. Capital I is the usual symbol for electric current, okay? So again, I'll point out that let's see, where are my colors here? Here we go. This is the charge transferred across the point that we're looking at, maybe through a wire, and this is the amount of time that it takes to do that. Time elapsed. Okay? So the definition of electric current is the amount of charge transferred per unit time. Example. Supposing 1 coulomb of charge, no, let me just make this a little bit more interesting. 120 coulombs of charge flows in a wire in 2 minutes. Find the current. Okay, do that now. If 120 coulombs of charge, I'll draw a little picture of this. 120 coulombs of charge flowing in a wire. So here's a wire. Big, thick wire. And the wire has, of course, lots and lots of charges in it, but I'll only represent that some of the charges are moving. And each one of these little charges we don't care about, but the total amount of charge that flows through this point in the wire, I will call big Q. Total amount of charge that flows out of the wire or that past that point, big Q, happens in 2 minutes. Calculate the current, and what does that come out to be?
1 coulomb per second.
Okay, 1 coulomb per 1 second, right? Per second. All right. That's basically what it means. 1 coulomb per second of charge. Now remember, a coulomb is a very large number of charges, right? Very large number of actual electron charges. Can't remember the number, but it's big. Now, this is given a special name, 1 ampere. So the unit of current is the ampere. One amp is equal to 1 coulomb per second. 1 amp, capital A is the symbol, is equal to 1 coulomb per second. You got lucky. I didn't really mean to make it come out perfectly like that, but there we go. Okay. Example. The ball that shuttles back and forth between the Van de Graaff generator and the other metal screen that I have there, similar to this picture. This ball coated with metal, as you know, was going back and forth between the positive and the negative parts of the setup that I had over there, right? You just saw it happening, bam, 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 bam. Well, I asked you, wow, why is it doing that? And the reason why, of course, is when it gets close, it kind of might need to be polarized. When you first turn it on, right, an electric field will exist in here. And that electric field, because this is a conductor, will cause this side to become positive and this to be negative, right? But it's still neutral. But then, when it has this polarization, it will then be pulled closer to the negative because and that's the thing, right? A neutral object can still be attracted to a charge and vice versa because one side of that neutral object is actually closer to the negative charge, right? And therefore, because of the inverse square law, its attraction is greater than the repulsion. So it moves this way, and because it is a conducting ball, it comes up, touches the negative, and what will happen? This is a conductor, and this is a conductor, so what's going to happen when two oppositely charged conductors meet?
The charge should cancel out.
Charge will become transferred, right? Now, that means that some electrons will go onto this ball. Now the ball will have a negative overall charge and go the opposite direction, right? And be attracted to the positive plate. Of course, this excess charge will then leave the positive plate until it actually probably becomes slightly positive, and then it will go back and the cycle repeats itself, and it goes back and forth over and over again. So the question is that basically, if this thing is bouncing back and forth at about 0.67 hertz, that is meaning that it does it almost 2 times a second, right? Okay, the frequency of this motion is about a little bit less than twice a second. The ball carries each time a magnitude of charge of 72 nanocoulombs each time that happens. So, given that information, what would be the average current that we might measure with an ammeter? An ammeter is an electrical device, a meter, that measures current, right? So we measure the current with an ammeter, and if this thing is happening fairly quickly, the ammeter will probably show an average value. Long story short, go ahead and calculate that, and calculate the number of electrons that are transferred every time the ball actually touches one of the plates, given the information that's there, okay? So go ahead and see if you can calculate first the average current in the circuit. Use the basic definition of current and then see how the given information can be used to fit into that. This problem isn't extremely challenging. Once you figure out how to do it, you just do it. But also part of this is to practice the units and getting the correct interpretation of the prefix. Hertz and as a unit, and maybe nano is a prefix, and what do you do with that? And make sure, even if you know what that means, that you can manipulate the numbers properly with your calculator and even writing them down correctly so that you don't make a mistake.
essentially how much is transferred. The ball carries a charge of magnitude 72.
So just divide.
The ball has a charge of 72, right? One is touched, they become neutral, so 0 again. So total touch force is equal to 72, right?
Because
So
most of the
Thomas?
right? So
Neutral.
it has 72, which is a swing from 0, and it's subtracted this one. 72, 0, 0.
Okay, anybody got an answer yet? No? No answer for A, average current in the circuit?
4.824 times 10 to the negative 8.
4.824 times 10 to the negative 8. Okay, let's see. All right, so how do you calculate current? What's the basic formula?
Q by T.
Okay, amount of charge transferred divided by the amount of time that it takes to do that. How much charge is transferred? Well, I guess if we just look at one oscillation of this thing, right? If we look at just one motion, just straight across one time, like that, how much charge is transferred? Okay, so that's our 72 nanocoulombs times 10 to the minus 9. Or I could have probably just left it with nano. Divided by the amount of time, delta T would be what?
1 divided by 0.7.
Right. So in other words, we gotta keep in mind that this is the frequency. Frequency is 1 over period. The period of time that it takes to transfer that charge, right? So T equals how many seconds?
1.49.
Okay, well actually 1.5, right? Oh, okay, I see what you're saying because this is actually rounded up, right? Okay, so 1.49 what?
Seconds.
No, when you, I'm just curious, when you did 1 over 0.67, was it exactly 1.49?
Oh no, it's 1.492537.
1.493?
Yeah.
Okay, so you're actually right. So it was actually 1.49, not 1.5, right? Correct? Okay. All right, so now we put in the amount of time, 1.49 seconds. And we divide 72 divided by 1.49, right? Equals how much? Approximately 72 divided by 1.5 almost.
4.824.
4.8. Okay, what I'm going to do is I say, oh, there's two significant figures here, so I'm just going to round two significant figures. 4.8
Times 10 to negative 8.
times 10 to the negative 8 coulombs per second. How many amps is that? Is that the same as 48 nanoamps? Could that be right? We could write it that way, right? Just if we wanted to. You don't have to. And B, the time, the minute, excuse me, how many electrons are transferred each time this happens? How many electrons are transferred each time this happens? How do we do that? Let's let n be the number of electrons. So how would you calculate the number of electrons that are transferred each time? Any idea of what you would multiply or divide or add or subtract, even if you don't know how to say it?
Maybe that ampere divided by 0.67.
The number of amperes divided by 0.67. Well, we know how much charge is evolved each time in coulombs, right? Shouldn't we use that? We're not interested in the frequency or time part anymore. Each time it happens, that much charge is transferred, right? So the total number of charges would be equal to the total charge involved divided by what?
Coulomb constant.
No, I don't think so. We want to find the number of electrons. And if we know the number of coulombs, what would we do to get that? What do we need to do? If I said that I have just transferred 50 boxes of ice cream sandwiches, and each ice cream sandwich has each box has 100 ice cream sandwiches, then how many ice cream sandwiches? So how do I relate that to this? I'm not even sure how I would relate it. I just confused myself.
We multiply the number of electrons.
Okay. Multiply by?
6.25 times 10 to the 18.
Okay. So 6.25 times 10 to the
18.
negative or positive?
Positive.
Oh, 18 electrons per coulomb, right? Okay, so it's the number of electrons in a coulomb, is what you're saying, right? All right. Basically, you are correct. What I might also say, because I already started writing it this way, looking at it just different direction, is that the total number of charges equals the total amount of charge divided by the charge per electron, right? The symbol E is a number just like pi, for example, and it's not a variable usually in these contexts, and it represents in electricity problems, it represents the charge on an electron. This is actually the fundamental charge. I think I talked about that before. The fundamental charge is the charge of one electron or one proton. In the case of an electron, it would be a negative. The number E, the value of E, is the charge on an electron equals how many coulombs? What is the electron charge? You can find it in the data or somewhere else where I've given it to you.
Oh,
1.6 times
Yep, 1.6 times 10 to the
negative
19 coulombs, okay? So, just as a reminder, this is the amount of charge on one electron, right? Expressed in coulombs. Why do I even bother mentioning E? Well, because it will come up again and again in other problems. In other situations, it's going to be more convenient to talk about fundamental charges because we're going to be dealing with the actual charges. One electron, one proton. So it's convenient. But the point is that right over here then, we have the total number of charges equals the total charge, this is measured in coulombs, I'll put a little C here, right? Divided by the charge on one electron. So we have our number, 72 times 10 to the minus 9 coulombs divided by 1.6 times 10 to the minus 19. Coulombs on an electron, and that should give us the answer for the number. Hopefully the same one you got just by multiplying by what you already said was the number of electrons per coulomb, right? It's the same math, just looking at it in a different direction. So what number does that come out to? The same one you got? Who's got a number for me?
1.5 times 10 to the 11.
Right. Okay, that's the number of electrons that are transferred every time that little ball moves back and forth. Quite interesting. 4.5 times 10 to the 11 is 450 billion electrons every single time that goes. Can you imagine all those things moving off in that short amount of time? Quite interesting. 450 billion electrons. Okay, do this one. Calculate the current in a wire through which a charge of 25 coulombs passes in 1500 seconds. Not a difficult one. Again, all of these charges, but 25 coulombs of charge leave the wire during a time period of 1500 seconds. So how much is the current? Practice by writing the formula down every single time so you can get it stuck into your head. This is, of course, an easy one. Song-hee, I equals what? What's the formula? Okay, amount of charge divided by the amount of time. So we have 25 coulombs divided by 1,500 seconds. And part of this problem is also about expressing the answer in a reasonable system of power of 10 or other units. So what do you get? 0, 1, 7.
6 repeated.
Okay. Amps. Got two significant figures here, so I guess stick with that. Okay. And what would be a way to express this in terms of what you might prefixes, SI prefixes, centi, kilo, etc. Or power of 10. In scientific notation, this is 1.7
10 to the power negative 2.
1.7 times 10 to the negative 2 amps. Say again? Something milliamps, but is that milliamps?
No, 17.
Aha, thank you. 17 milliamps is a very nice way to put that too, okay? Because you'll see that very common use. Why do we sometimes use milli, other times other things? Tradition. How much charge flows in a wire in 1 minute if the current is 36 milliamps? So this time, slightly different approach to the problem. So we have a wire, we have an ammeter that is reading the current, which I will stick here just for fun. This is the symbol for an ammeter, and the ammeter is telling us that we are getting 36 milliamps in this wire. Why? Well, maybe this is hooked to a battery. Here's the symbol for a battery. Starting to introduce some of these symbols to you, okay? I said battery. Of course, I should probably say cell, right? But I'll write the word battery anyway. Okay. Karan, how do we do it? How do we do it?
Q equal I times T.
Yep, that's all. Q equals I times T. Q, well, of course, we start with I equals Q divided by T, solving it for Q equals I times T. Do I have to use delta T? No. Technically, on some problems, it might make more sense to do that, but T is the amount of time. Okay, and therefore, we have current 36 milliamps times 60 seconds. What's the answer, Karn?
2.16.
2
I didn't write.
point
2.2.
2 times anything? Okay. So the answer is in fact 2.2 what? Okay, coulombs. So therefore, one of the things you want to keep in mind is that current times time equals charge. Because an amp is a coulomb per second, right? All right, so talked about current, we've talked about how to calculate it and what's going on inside of a wire, and we briefly touched on what makes it happen, right? What makes a current actually happen. And that was the electric field, right? And we talked about, well, how do we make such an electric field? And we said we had to have a charge separation probably somewhere to do that. So a battery or other source of electricity makes a current by making an electric field caused by charge separation. I told you it was important. And the direction in a circuit of the flow or a wire or any conductor, the direction of the flow of charges, well, what direction is it? How can you describe that direction based on what you know about electricity? Mentioned it earlier. Well, the direction, it depends on what kind of charge it is, right? Okay? Yeah. Okay, so if the charges are electrons, they have a negative charge, okay? And so therefore, the direction of the actual flow of actual charges depends on if they're positive or negative. But for electrons, here's a wire, and the wire has a negative side and a positive side. For whatever reason, charge separation, we created it. And we know that the flow of the electrons will be in this direction. From negative to positive is the actual electron flow. But you might imagine that in the days before people knew that it was electrons that flow, before they knew that electrons were the charge carriers in current, and before they knew that such charge carriers that were flowing were negative, the presumption was that, well, all they talked about was, oh, charge is flowing. It's flowing because we're assuming that it's positive, perhaps, right? If you had no idea, you would probably just assume that something's flowing, and you would probably assume that the positive one is maybe going one way, and negative one's opposite of that, but we'll just calculate everything with the positive numbers, right? Everybody likes to calculate positive numbers more than negative numbers. So this developed what we call the so-called conventional current. Conventional current is the flow of current or charge if charge carriers were positive. That is to say, the conventional current is the current that we calculate with all of the time, almost all of the time, in electricity, and it presumes a positive charge flowing. It is not real in a sense that positive charge is actually flowing in a wire. True enough. However, the mathematics of it end up being exactly the same. A positive charge flowing to the left would be equivalent to a negative charge flowing to the right in terms of every electrical effect that you can imagine, okay? And so therefore, the conventional current I is what we will show on our diagrams and what we will calculate in all of our problems, and is what we will call the current, okay? Unless stated otherwise, we will use conventional current, and only in problems where specifically electron flow is mentioned, then we might talk about actual electron negative current, okay? So in a circuit, keep in mind then, I'll draw a picture of a circuit here. Supposing we have a battery or cell, and we have a light bulb in our circuit, which I will draw with this symbol right here. Then we know that for whatever reason we have this cell producing an electric field in the wire. The electric field in the wire is going in this direction, you see. So it doesn't matter what charges are actually flowing, you can't get away from the fact that the electric field is in that direction, right? So doesn't it make sense, since we're dealing with real physics, with real electric fields, with real specific directions, that, well, the electric field's that way, and we're going to make the current the same way. Because positive charges would flow that way. That's the only reason why we do it that way. Plus tradition. If you had switched early on to negatives flowing in circuits, and putting the negative current, all of our equations and calculations and results and predictions and everything would have been opposite and would have been correct, but they would only refer to those things. They all end up, it's like, imagine all of the negative signs that would have shown up in formulas. Well, most of them would have canceled out, right? Negatives times negatives, divided by negatives, multiplied by negative. Negative times a negative makes a positive. So in the end, the risk of confusing you even more, all I'm saying is that in the end, it doesn't make any difference. So we say that the current I, flows in a circuit, or the current is in a circuit. Current doesn't flow, charge flows, in this direction. This is the conventional current. Notice that I have it going from positive. This is the positive terminal, and this is the negative terminal of our cell. So what I have just taught you, just in case you're wondering when this is going to end, is what is conventional current? How do we indicate the fact that if a conventional current is in a particular direction, and why we chose that? Because of the electric field in the wire, and also because it just makes all the calculations come out a little bit easier to work with, because eventually all those negative signs are going to cancel anyway. And I think I'm going to stop here because this next topic is pretty complicated, okay? So we're going to pause, stop, and I guess we could chill out for a couple minutes. You want to do that? All right. It is Thursday before Labor Day. I will put several things on Manage Back over the next week, one of which will be definitely today. The school is officially not over until the end of the day. And it will be the rest of this lesson, a video style, maybe music, I don't know, probably not. And with some homework problems associated with that and what we're doing today, okay?